This is AQA GCSE Chemistry. It is a triple only section of the chemical calculations topic. We're going to take a look at atom economy calculations. If you're doing dual award, you don't need to look at it. I'm going to recommend, as always, that you pause as you go, have a go at the questions for yourself. So let's take a look. Atom economy, doing atom economy calculations from balanced equations and understanding why it's important industrially. So we've got the process here. This is what we do. The relative formula mass of desired product in the equation divided by the sum of the relative formula masses of all reactants in the equation. And we multiply that by 100 and it becomes a percentage. We have a worked example here where I am making C2H5F chloroethane and I want to know what percentage atom economy there is. Its MR is 48 and the total MR of all of the reactants is 66. So my atom economy is 48 over 66 multiplied by 100, 73%. Now, atom economy is important because the higher it is, the more profitable an industrial process might be, for example. It's certainly more efficient, though you can't change the atom economy of a reaction. So let's take a look at some examples for you to try. And in this first example, we're interested in the atom economy of tungsten in reaction of tungsten oxide with hydrogen. Well, tungsten has got a relative atomic mass of 184 and the total for WO3 and 3H2 is 184 plus 48 plus 6. So 184 divided by this multiplied by 100, we get an atom economy of 77.3%. Let's look at the next example. And in this one, we want to know the atom economy of copper. That's the useful product. So copper, I'm making 2 moles of it. So it's 2 multiplied by 63.5. And then on the other side, my 2Cu, CO3 and C add up with all of these atomic numbers or atomic masses here. So when I put those figures in, I get a percentage atom economy of 49.03%. Next example for the extraction of titanium. Now, titanium has a mass number of 48, and when I add up all of these ones, you can see that's much, much higher. 48, I've got 4 chlorines at 35.5 each, I've got 4 sodiums at 23 each. When I do that calculation, it comes to just 17.05%. Now, industrially, that is not good. It means that there is a huge amount of waste there. But NaCl could be sold on to make some extra profit. So one way round a poor atom economy is to find uses for the waste products. On to the next one. And in this case, we're interested in the NaClO, which is 23, 35.5 and 16. My total for sodium hydroxide, I've got 2 of them, so that's 2 40s, 71 for Cl2. I put all of those figures in and it comes to the value 49.34%. Final question. And this is looking at 2 alternative methods, and you might want to think about industrially which of them you would use. Well, actually, if I take the first one, I have an atom economy of 100%. It means there's no waste product at all. But on the second one, it's only 78%. Now, it is definitely industrially advantageous to get the higher atom economy. To get 100% atom economy is absolutely fantastic. Do be aware that this is different to percentage yield. We might not get 100% percentage yield on that reaction. There might be impurities, there might be some lost. You've got to consider these as 2 very separate and very distinct calculations. Learn percentage yield, learn atom economy, and do not put the 2 together. That takes us to the end of this video. Thank you for listening, and goodbye.